below. In this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and this square. We know that the radius of the small circle is equal to 1 unit. The radius of the circle, the side length of the square is equal to 3 units. And our mission is to find out the radius of this big circle. Okay, so first of all, we'll define the vertex of the triangle. This vertex is A. We'll define this vertex as B. And we'll define this vertex as C. Actually, this is a triangle, although in the drawing it does not look like a triangle, but it is a triangle. So look at this drawing as a triangle. Okay, we define the point of tendency of tangent BC with this small circle as point D. We will define the touching point of the square with side BC as E. We define the second touching point of the square with side BC as F. We will define the point of tendency of the square with the circle as G. We will define the touching point of side AC with the square as H. We define the point of tendency of tangent AC with the small circle as J. We define the point of tendency of the square with the circle as K. We define the point of tendency of tangent AC with this circle as L. We define the point of tendency of tangent BC with this circle as L. We define the center of the big circle as P. And we define the center of the small circle as O. Okay. In the next step, we join points O and G together by a straight line. Point O is the center of the circle. Point G is the point of the circle itself. Therefore, OG is the radius of the small circle that is equal to R. And the radius of the small circle is equal to 1 unit, according to what is given as the question. So here we have the radius OG that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to each point of tendency. This angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius OD that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have the radius PL that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, so we know that all the angles inside the square are right angles, so this angle equals to 90 degrees. This angle will be also equal to 90 degrees. This angle equals to 90 degrees. And finally, this angle will be also equal to 90 degrees. And We also have here rule number 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. Side BC of triangle ABC as a side of a triangle it is absolutely a straight line. So BC is a straight line. So if we focus on the upper side of the straight line BC at point F, here, according to rule number 3, the sum of the angles here must be equal to 180 degrees. So which angles we have at the upper side of BC at point F? We have this angle that is equal to 90 degrees plus the mean sin angle. In total, they must be equal to 180 degrees. So this angle must be also equal to 90 degrees. Okay. In order to complete the sum of the angles on the upper side of BC at point F to 180 degrees, this angle must be also equal to 90 degrees. Likewise, if we focus on the upper side of BC at point E, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees according to rule number 3. So inside quadrilateral OGED, this quadrilateral, we have 1, 2, 3 right angles. Again, inside quadrilateral OGED, we have 1, 2, 3 right angles. And the sum of 3 right angles is 270 degrees. So the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any triangle is equal to 360 degrees. So therefore quadrilateral GOED that has 4 right angles, we relate to it as a rectangle. I write it down. Quadrilateral GOED is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. So that is to say, GO equals to ED. GO equals to ED. Here, GO equals to ED. But here, GO equals to 1 unit. It is the radius of the small circle. So I can write here that GO equals to 1. And from this equation, 1 equals to GO equals to ED, we derive that ED is also equals to 1 unit. ED equals to 1 unit. ED equals to 1 unit. Here we can write down that ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that GE equals to OD. GE equals to OD. GE equals to OD. But here OD equals to 1 unit. It is the radius of the circle. OD equals to 1, and from this equation GE equals to OD equals to 1, we will derive that GE is also equals to 1. GE equals to 1. Yeah, GE is also equals to 1 unit. So actually we found out that quadrilateral GOED is not a rectangle but a square. Okay. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point P. From the common external point P, we have two tangents to the second, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule number 2 in our drawing. Why? Because in our drawing we have the common external point H. From the common external point H, we have two tangents to the second, tangent HG and tangent HJ. And according to rule number 2, they are equal to each other. That is to say, HG equals to HJ. Here, HG equals to HJ. What is the value of HG? HG equals to HE minus GE. That is to say, HE is 3 units. It is sine length of the square, that is 3 units, minus GE, that is 1. So 3 minus 1 is 2. So HG equals to 2 units. So for this equation, 2 equals to HJ equals to 2 equals to HG equals to HJ, we derive that HJ is also equals to 2 units. Likewise, if you focus on the common external point C, for the common external point C, we have two tangents to this second, tangent CJ and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CJ equals to CD. So if we define CJ as x, then CD must be also equal to x because of the fact that they are equal to each other. Okay, so in the next step, we'll implement the Pythagoras theorem on the right green triangle HCE. On the right green triangle HCE, here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, HC square equals to HE square plus EC square. Repeat again, in the right green triangle HCE, according to the Pythagoras theorem, HC square equals to HG square plus EC square. So what is the value of HC? HC equals to 2 plus x. Therefore HC square equals to 2 plus x square. And it is equal to HE square. HE equals to 2 plus 3, that is 2 plus 1, that is 3. Therefore, HG square is 3 squared, that is 9, plus EC square. What is the value of EC? Here, EC equals to 1 plus x. Therefore, EC square is equals to 1 plus x square. So in conclusion, we found out that according to equation number 1, 2 plus x square equals to 9 plus x plus 1 square. So here we'll open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, two plus x squared equals to 2 squared, that is 4, plus x squared, plus 2 times 2x, that is 4x, that is equal to 9 plus x plus 1 squared is equal to x squared plus 1 squared, that is 1, plus 2x. So here we have x squared on both sides of equation number 1, so x squared will get cancelled. So what is left from equation number 1 after we cancel x squared? In this side of the equation we left only with 4 plus 4x, that is equal to 9 plus 1 is 10, plus 2x. Here we subtract 4 from this equation, equation number 1, and we get that according to equation number 1, 4x equals to 10 minus 4 is 6, plus 2x. Here we subtract 2x from this equation, equation number 1, and we get that according to equation number 1, 4x minus 2x is 2x, that is equal to 6. Here we divide this equation, equation number 1 by 2, and we get that 6, x equals to 6 over 2, that is 3. So I found out that x equals to 3 units, and right here that x equals to 3 units, and there also x equals to 3 units. Okay. In the next step, we join points O and J together by a straight line. Point O is the center of the small circle, point J is the point of the small circle itself, therefore OJ is the radius of the small circle, that is equal to 1. R equals to 1, small r equals to 1. In the next step, we join points C and O together by a straight line. By joining points C and O by a straight line, we created there 2 right triangles. Here, this angle actually equals to, we have the radius that is born to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees. So we have here 2 right triangles, triangle OCD and triangle OCJ. Repeat again, we have triangle OJC and triangle ODC. So we prove that those 2 right triangles can relate to each other according to side rule. So I write it down. We prove that the right triangle JOC is converted to the right triangle, triangle ODC. So why those 2 right triangles convert to each other? First of all, JO equals to OD, they are equal to each other because they are both the radii of the circle, therefore they are equal to each other. So JO equals to OD equals to R, that is equal to 1. In addition, we have here CJ equals to CD, they are equal to 3 units, according to rule number 2. CJ equals to CD, they are equal to 3 units, according to rule number 2. And finally, we have side CO, that is the common side that belongs to both triangles, so CO equals to itself. It's the common side that belongs to both triangles. So we actually found out that the 2 green right triangles can go into each other according to side rule. And for the fact that the 2 right triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay. In the next step, we'll join points J and D together by a straight line. Here we created triangle JDC. So, according to what we did until now, we can conclude that CO is the angle bisector of angle C. I'll write it down. CO is the angle bisector of angle C. This angle C. In triangle JDC. I'll repeat again. CO is the angle bisector of angle C in triangle JDC. Why? Because it bisects angle C into two equal halves, theta and theta. In the next step, we'll join points P and L together by a straight line. Here, point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that is equal to capital R. We join points C and P together by a straight line. When joining points C and P together by a straight line, we created here two right angles. Here we have the radius that is drawn to the point of tendency. For that reason, this angle equals to 90 degrees, and this angle will also equal to 90 degrees. We have here two triangles, two right angles, triangle PLC and triangle PLC. So here we define this angle. We have two points with the same name, so we define this point as point S. We will prove the triangle PSC, the right triangle, although it does not look like a triangle, you should relate to it as a triangle. PC, triangle PSC, this right triangle congruent to the right triangle, triangle PLC. So why those two triangles can go to each other? First of all, PS equals to PL. They are both the radii of the circle, therefore they are equal to each other. PS equals to PL equals to capital R. In addition, we focus on the common external point C. For the common external point C, we have two tangents to the big circle, tangent CS. I repeat again that we relate to CS as a straight line. It does not look like that in the drawing, but it's the problem of the drawing, but we relate if CS is a straight line. So we have tangent CS and tangent CL. So here CS equals to CL according to rule number 2. CS equals to CL according to rule number 2. And finally, we have side PC, that is a common side that belongs to both triangles, so PC equals to itself. PC equals to PC, it's a common side that belongs to both triangles. So we actually proved that those two big right triangles can go into each other according to side rule. And from the fact that the two right triangles can go into each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta, while because of the fact that they are equal to each other. So here we join points S and L together by a straight line. Here we create a triangle LSC. So here, according to what we did until now, we can conclude that CP is also the angle bisector of angle C. CP is the angle bisector of this angle C, in triangle LSC. Okay, again, CP is the angle bisector of angle C in triangle LSC. It bisects angle C into two halves, theta and theta. So actually, we found out that angle C is two angle bisectors, CO and CP. Okay. In the next step, we'll prove that CO passes for point P. Again, we'll prove that CO passes for point P. So our claim is that the angle bisector CO passes for point C, for point P, for this point P. Okay, again, our claim is that CO passes for point P. We'll prove this claim in a negative way. In a negative way, assume that CO doesn't pass for point P. So our assumption is that CO doesn't pass for point P, and due to our assumption we will arrive to a contradiction, and because of the contradiction we conclude that our assumption is not correct, and therefore CO must pass for point P. This is the process of the proof. Okay. So if CO doesn't pass for point P, then we will have here angle DCO that is equal to theta. So here angle DCO this is angle DCO or OCD, it doesn't matter, that is equal to theta. Okay. And it is very easy to see from the drawing that CD is part of CB. Again, CD is part of CB. And because of the fact that CD is part of CB, you can say that CD and CB are located on the same straight line. CD and CB are located on the same straight line. In the next step, I will draw angle PCB. Okay, I will draw angle PCB. So this is angle PCB that I drew from the original drawing. We already found out that leg CD on this angle and leg CB on this angle They are both located on the same straight line. CD and CB, they are located on the same straight line. What about the second leg of the two angles? I mean, relate to leg OC and leg PC, that is the second leg of those two angles. Here the second leg, according to our assumption, CO doesn't pass for point P. If CO doesn't pass for point P, it means that CO and CP, they are not located on the same straight line. Okay, if CO doesn't pass for point P, it means that CO and CP are not located on the same straight line. Okay, otherwise CO must pass for point P. Okay, if CO is located on the same straight line as CP, CO must pass for point P, but according to our assumption, CO doesn't pass for point P, therefore CO and CP are not located on the same straight line. So I write it down. So the second leg of those two angles, CO and CP are not located on the same straight line according to our assumption, of course. So we have here two angles that one of their legs are located on the same straight line, while the second leg of those two angles are not located on the same straight line. That is to say, those two angles can never be equal to each other. Why? Because in order to be equal to each other, if the first leg is located on the same straight line, then the second leg also must be located on the same straight line. But according to our assumption, the second leg doesn't located on the same straight line. Therefore, we actually found out that, so if this angle is theta, this angle is alpha, and alpha is not equal to theta. So we actually found out that angle C has two different angle bisectors. That is to say CO and CP that bisect it into two different halves. While the angle bisector CO bisect angle C into two halves that are equal to theta and theta, angle bisector CP bisects angle C into two different halves that are equal to alpha and alpha. And this is absolutely impossible. Why? Because if angle C is equal to 30 degrees, then any angle bisector will bisect it into two will bisect it into two halves that are equal to 15 degrees and 15 degrees only, and not to any other halves. But here we have two different halves that angle C will be bisected. And it is impossible, so we have a contradiction, and due to the contradiction, we will conclude that our assumption that CO doesn't pass through point P is incorrect. Therefore, if our assumption is incorrect, so the opposite field will be correct. That is to say, CO indeed passes for point P. Okay, we finished the proof. In the next step, we focus on the right angle triangle ODC. This angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle here will be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle, and especially in triangle ODC. Likewise, in triangle PLC, the right triangle, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. So in the next step, we will prove that those two right triangles are similar to each other. Triangle PLC is similar to the small green triangle, triangle ODC. Here I write it down. We'll prove that triangle, the big right triangle, triangle PLC, is similar to the big right triangle, to the small green right triangle, triangle ODC. So why those two triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I can write down that angle LPC in the big right triangle is equal to this angle, this is actually angle COD. So again, angle LPC equals to angle COD. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, we have those two angles that they are both equal to 90 degrees, therefore they are equal to each other. So angle PLC is equal to this angle that is actually angle ODC. Repeat again. angle PLC equals to angle ODC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle theta. This angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. So angle theta equals to angle PCL and we can call triangle theta also angle OCD. Repeat again. Here, angle theta equals to itself. It's a common angle that belongs to both triangles. We actually proved that the big triangle PLC is similar to the small triangle ODC according to angle similarity rule. So I write it down. Triangle PLC, the big right triangle, is similar to the small green right triangle, triangle ODC, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that PL in the big right triangle over OD in the small green right triangle is equal to LC in the big right triangle over DC in the small green right triangle. I'll repeat again. We derive from the fact that those two right triangles are similar to each other that PL over OD equals to LC over DC. PL equals to R, it is the radius of the big circle, over OD. OD equals to 1, it is the radius of the small circle, and it is equal to LC. What is the length of LC? LC equals to 3 plus 1 plus 3, that is 7, plus LF. So in total, LC equals to 7 plus LF. 7 plus LF over DC. Here DC equals to X, that is equal to 3 units. Here, DC equals to 3 units. So we substitute DC by 3. So in conclusion, we found out that according to equation number 1, R equals to 7 plus LF over 3. We multiply this equation number 1 by 3, and we get that according to equation number 1, R equals to NF plus 7. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, LF equals to 3R minus 7. And F equals to 3R minus 7. And write in the drawing that LF equals to 3R minus 7. because of the fact that the side length of the square is equal to 3 units, we will examine three possibilities for the radius that we are looking for the radius of this big circle. We will examine the possibility that the radius of this big circle, capital R, is less than 3 units. We'll examine the possibility that R equals to 3 units exactly. We'll examine the possibility that R is greater than 3 units. Okay, we start with the first case. So, if R is less than 3 units, so we will have a circle with a radius that is less than 3 units. If this radius is less than 3 units, it means that the square itself will be higher than the radius. The side length of the square will be higher than the radius. Okay, so the square here that we have in the drawing will be higher than the radius. Side length of the square is equal to 3 units, and it is higher than the radius. Here this is the square, each side is equal to 3 units. From the angles here are right angles. So the radius, here, this is the radius. We know here, this is the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay. So we have here, this is point P, this is point L, this is point F, this is point K. We'll define the point of tendency of tangent P of the radius with the side length of the square as point T. Actually, in quadrilateral PTLF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So in quadrilateral PTLF, we have 4 right angles. Therefore, quadrilateral PTLF is a rectangle because it has 4 right angles. And the opposite sides of a rectangle are equal to each other. That is to say, here PT is equal to LF. LF equals to 3R minus 7, according to what we have already found out. So here PT equals to LF. But here PT is the radius of the circle, so we can write here that PT equals to R. And from this equation, R equals to PT equals to LF, we will derive that LF is equal to R. From one side, LF equals to R. From the other side, LF equals to 3R minus 7, according to what we have already found out. And from this equation, R equals to LF equals to 3R minus 7, we will derive that R equals to 3R minus 7. Here we subtract R from this equation, and we get that R minus R is 0. 3r minus r is 2r minus 7 equals to 0. We'll add 7 to this equation and we get that 2r equals to 7. We'll divide this equation by 2 and we'll get that r equals to 3.5 units. R equals to 3.5 units, but according to our assumption, R is less than 3 units. R is smaller than 3 units. R cannot be both equal to 3.5 units and also less than 3 units, so due to the contradiction, we conclude that R cannot be less than 3 units. The second possibility that we have for the value of R is that R is equal exactly to 3 units. So the second case is R equals to 3 units. So if R equals to 3 units, we have the radius of this circle is exactly equals to 3 units, so R equals to 3 units. And the side length of the square is also equals to 3 units. So the radius of and the side length of the square will be in the same height. Here R equals to 3 units. This is the side length of the square that is also equals to 3 units. According to rule number 1, we have the radius that is drawn to the point of tendency, therefore this angle equals to 90 degrees. Okay, so here we have P, L, F, K. So here quadrilateral PLFK is 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral PKLF has 4 right angles. Therefore we relate to quadrilateral PKLF as a right angle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PK is equal to LF. PK equals to LF, but here PK equals to R equals to 3 units. So we can write here that PK equals to 3. From this equation 3 equals to PK equals to LF, we will derive that LF is also equals to 3 units. From one side, LF equals to 3 units. From the other side, LF equals to 3 R minus 7, according to what we have already found out. So, from this equation, 3 equals to LF equals to 3 R minus 7, we derive that 3 R minus 7 equals to 3. Here we add 7 to this equation, and we get that 7 plus 3 is 10 equals to 3R. 10 equals to 3R, we divide this equation by 3. And we will get that R equals to 3 and a third. But according to our assumption, R equals to 3. R cannot simultaneously be equal to 3 and a third. So due to the contradiction, we'll cancel this possibility. R cannot be equal to 3 units. So we left only with the last possibility, that the radius of this circle is greater than 3 units. Here the radius is greater than 3 units. So here, this is the radius. Therefore here, the radius will be higher than the side length of the square. So here, from point K, we draw perpendicular on the radius PL. From point K, we draw perpendicular on the radius PL. So here, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. According to our construction, we define the touching point of the perpendicular from point K and PL as T, and F equals to 3R minus 7. So inside quadrilateral TKLF, inside this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral TKLF that has 4 right angles, we will relate to it as a rectangle. I write it down, quadrilateral TKLF is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. So that is to say, here TL equals to KF. Here TL equals to KF. Okay. But here KF is the side length of the square that is equal to 3, and from this equation 3 equals to TL equals to KF, we will derive that KF is also equals to 3. Here KF equals to 3. And here, actually here 3 TL equals to KF, but we know that KF equals to 3. We know that KF equals to 3. From this equation, TL equals to KF equals to 3. We derive that TL is also equals to 3. Okay? TL is also equals to 3. Here TL equals to 3. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that TK is equal to LF. But we know that LF equals to 3R minus 7, so we can write here that LF equals to 3R minus 7. And from this equation, TK equals to LF equals to 3R minus 7, we derive that TK is also equals to 3R minus 7. TK is also equals to 3R minus 7. What is the value of PT? It's very easy to see from the drawing. That PT is equal to PL minus TL. Again, PL minus TL equals to PT. So PT equals to PL minus TL. That is to say, PT equals to PL is the radius of this big circle that is equal to R minus TL. TL equals to 3. So in conclusion, we found that PT equals to R minus 3. So in the next step, I'll copy, we'll join points P and K together by a straight line. Here point P is the center of the circle, point K is the point of the circle on the circle itself, therefore PK is the radius of the circle that is equal to R. So in the next step I will copy the right green triangle PTK in a new page, and we will implement the Pythagoras theorem right green triangle, triangle PTK. Okay. So this is the right triangle, triangle PTK. This is the copy from the original drawing. We'll implement the Pythagoras theorem in this triangle. So here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, the square of the hypotenuse is pk squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to pt squared plus dk squared. Okay, pk equals to r, therefore pk squared is r squared. That is equal to pt squared. Pt equals to r minus 3, therefore pt squared is r minus 3 squared plus tk squared. Tk equals to 3r minus 7, therefore tk squared equals to 3r minus 7 squared. Here we'll open the brackets on this side of equation number 1, and we get that according to equation number 1, r squared equals to r minus 3 squared is r squared plus 3 squared, that is 9, minus 2 times r times 3 is minus 6r plus 3r minus 7 squared. It is equal to 3r squared, that is 9r squared, plus 7 squared, that is 49, minus 2 times 3r is minus 6r, and minus 6r times 7 is minus 42r. So here we have r squared on both sides of equation number 1, therefore r squared will get cancelled. What is left from equation number 1 after we cancel r squared? In this side of the equation, nothing is left, so we have 0. Here we have 9r squared minus 42r minus 6r is minus 48r, and 9 plus 49 is plus 58. So we have here a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Okay, in our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58. And the variable that we are looking for is r, so x equals to r. So we'll put the data inside the equation for x and we'll find out the value of the values of r because x equals to r. So r equals to minus b. b is minus 48, so minus b is minus 48, that is plus 48, plus minus square root of b squared. b is minus 48, so b squared is minus 48 squared, that is 2304 minus 4 times a is 9, so minus 4 times 9 is minus 46, and minus 46 times c is 58, so minus 36 times 58 is minus 2088 over 2a. a is 9, so 2a is 18. So here we get that r equals to 48 plus minus 2304 minus 2088 is 216 over 18. So here we have two solutions that are possible for r. The first solution for r is that r equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here r equals to 48 minus 4. Here it is minus, of course. 48 minus 14.6969 is 33.3031 over 18, and 33.3031 over 18 is 1.85. So I found out that the radius of the big circle is equal to 1.85, but we already found out that the radius of the big circle cannot be less than 3 units, and 1.85 is less than 3 units. Therefore, we cancel this possibility and we're left only with the second possibility for r, that r equals to 48 plus 14.6969 over 18. So here r equals to 48 plus 14.6969 is 62.6969 over 18. 62.6969 over 18 is 3.483 units. Okay, so we actually found out that the radius of this big circle r is equal to 3.483 units. Okay, r equals to 3.483 units. We finished with the question. In the next step, I will summarize the lecture. Actually, in the drawing, we have a big triangle. Inside the big triangle, we have two circles and one square. And the radius of the small circle is equal to 1 unit. The side length of the square is equal to 3 units. And our mission is to find out the radius of this big circle. Okay. So actually, I presented to you 3 rules that we used all over the solution to the question. So I will repeat on the 3 rules that we used during the solution of the question. We have rule number 1. According to rule number 1, we tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? Then I presented to you rule number 2 also. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. And then I presented to you rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. Here CD is a straight line. So if you focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have angle alpha and angle beta. And according to this rule number 3, alpha plus beta must be equal to 180 degrees. Okay, we use those three rules in order to solve the question. By using these three rules, we actually concluded that quadrilateral GOED, this small quadrilateral, is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, GO equals to ED. GO equals to ED. But here GO equals to 1 unit. It is the radius of the circle, of the small circle. GO equals to 1, and from this equation 1 equals to GO equals to ED, we derive that ED is also equals to 1 unit. ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OD equals to GE. OD equals to GE, but here OD equals to 1 unit, it is the radius of the circle. And from this equation, GE equals to OD equals to 1, we derive that GE is also equals to 1 unit. Here, GE equals to 1 unit, so actually found out that quadrilateral GOED is not a rectangle, but a square, because all of its sides are equal to each other, they are equal to 1. Okay, then we actually used rule number 3. We have BC is one side of triangle ABC, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line BC at point F, here the sum of the angles must be equal to 180 degrees. So if this angle equals to 90 degrees, then this angle must be equal to 90 degrees in order to complete the sum of the angles on the upper side of BC at point F to 180 degrees. This angle must be equal to 90 degrees. So if you focus on the upper side of the straight line BC at point E, the sum of the angles must be equal to 180 degrees according to rule number 3. Which angles we have in the upper side of BC at point E? We have here 90 degrees. So this angle must be equal to 90 degrees. Exactly for the same reason, then this angle equals to 90 degrees. Okay, then use rule number 2 here. If we focus on the common external point, point H, we have two tangents to this circle, tangent HJ and tangent HG. And according to rule number 2, they are equal to each other. That is to say, AG equals to HJ. AG equals to HJ. But here, what is the value of HG? HG equals to 3 plus 1, that is 2. And for this equation, 2 equals to HJ equals to 2 equals to HG equals to HJ, we derive that HJ is also equals to 2 units. Likewise, if we focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CJ and tangent CO. And according to rule number 2, they are equal to each other. So if we define tangent CJ is X, then tangent CD must be also equal to each other because of the fact that they are equal to each other according to rule number 2. Okay, then implemented the Pythagoras theorem on the green right triangle, triangle AEC. This green right triangle The square of the equators equals to the sum of the square of the perpendiculars. That is to say, HC square equals to HE square plus EC square. In the right triangle HCE, HC square equals to HE square plus EC square. What is the value of HC? HC equals to 2 plus x. Therefore, HC square equals to 2 plus x square. What is the value of HE? HE equals to 2 plus 1. That is 3, and HE square is 3 squared, that is 9. What is the value of EC? EC equals to 1 plus x. Therefore, EC square equals to 1 plus x square. Okay, so actually found out that according to equation number 1, 2 plus x square equals to 9 plus x plus 1 square. We open the brackets on both sides of equation number 1. We found out that according to equation number 1, 2 plus x square equals to 2 squared, that is 4, plus x square, plus 2 times 2x, that is 4x, and it is equal to 9 plus x plus 1 square. X plus 1 square equals to x square plus 1 plus 2x. Here we have x square on both sides of equation number 1, so x square will get cancelled. What is left from equation number 1 after we cancel x square? What is left is that in this side of the equation we have 4 plus 4x. And the other side of the equation we have 9 plus 1, that is 10, plus 2x. We subtracted 4 from this equation, equation number 1, and we found out that 4 minus 4x equals to 10 minus 4 is 6, plus 2x. We subtracted 2x from this equation, equation number 1, and we found out that 4x plus 2x is 2x, and 2x equals to 6. Here we divided this equation, equation number 1 by 2, and we got that x equals to 6 over 2, that is 3. So here x equals to 3 units, x equals to 3 units. Okay, then actually joint points O and E together by side 9. Here we joined points O and J together by side 9. Point O is the center of the circle, point J is the point of the circle itself, therefore OJ is the radius of the circle. Then we joined point C and O together by side 9. We created here 2 triangles. We proved that those 2 triangles can go into each other according to side O. I'll explain what I mean here. JO equals to OD. They are equal to each other because of the fact that they are the circle, therefore they are equal to each other. In addition, CJ equals to CD. They are both equal to 3 units, therefore they are equal to each other. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. We actually proved that those 2 green eye triangles are congruent to each other according to side rule. And from the fact that those 2 eye triangles are similar to each other, we derived that those 2 angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those 2 triangles are congruent to each other, therefore those 2 corresponding angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Then we joined points J and D together by side 9. And here we can conclude from what we did until now that CO is the angle bisector of angle C. Here CO is the angle bisector of angle C. We bisect angle C into 2 halves. Each half equals to theta in triangle JDC. Here CO is the angle bisector of angle C in triangle JDC. Then we joined points P and S together by side 9. Point P is the center of the circle, point J is the point of the circle itself, therefore PJ is the radius of the circle that is equal to R. Then we proved that those 2 big right triangles can go into each other according to side rule. I'll explain what I mean. Here, SP equals to PL, above the area of the circle, therefore they are equal to each other. If we focus on the common external point C, from the common external point C, we have 2 tangents to this circle, tangent CS and tangent CL, and according to rule number 2, they are equal to each other. That is to say, CS equals to CL. And finally, CP is the common side that belongs to both triangles, so CP equals to itself. So we actually proved that those 2 right triangles can go into each other according to side rule. And from the fact that those 2 right triangles can go into each other, we derived that those 2 angles are equal to each other according to the rule that the corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So we actually then join points S and L together. So here we can conclude from what we did until now that CP is also the angle bisector of angle C. Why? Because CP bisects angle C into two halves, theta and theta. So angle C has two angle bisectors. Angle bisector CO and then angle bisector CP. Then we have the claim that CO passes through point P. CO passes through point P. CO passes through point P. We proved this claim in a negative way. We assumed that CO doesn't pass through point P. By this assumption, we got to a contradiction, and therefore we concluded that CO must pass through point P. Okay. So here according to our assumption, we have here angle DCO that is equal to theta. This is angle DCO that I copied from the original drawing. It is very easy to see from the drawing that CD and CB, or CD is part of CB. If CD is part of CB, it means that CD and CB lie on the same straight line. Okay? Here, CD and CB are located on the same straight line. Why? Because CD is part of CB. Okay? Then I copied. So this angle OCD equals to theta, then I copied angle PCB, this new page, angle PCB. So those two angles have one leg that is located on the same straight line. Here, CD is located on the same straight line as CB. So we can see it as one leg of those two angles that is a common leg, okay? And what about the second leg of those two angles? The second leg, this is CO is the second leg of this angle, and PC is the second leg of this angle. According to our assumption, CO doesn't pass through point P. If CO doesn't pass through point P, it means that CO and CP are not located on the same straight line. Very simple. Otherwise, if CO and CP are located on the same straight line, CO must pass through point C. But according to our assumption, CO doesn't pass through point P. Therefore, CO and CP are not located on the same straight line. Okay, CO and CP are not located on the same straight line. So we have here two angles that have one leg that is a common leg, because this leg, the first leg of those two angles, are located on the same straight line, and the second leg is not located on the same straight line. Therefore, they must be different angles. If one leg is located on the same straight line, in order that those two angles will be equal to each other, the second leg must be also located on the same straight line. But the second leg is not located on the same straight line according to our assumption. So we actually found out, so if this angle is theta, then this angle is alpha, and alpha is not equal to theta. Those are two different angles. So actually, in conclusion, we found out that angle C, this angle C, has two different angle bisectors that are CO and CP that bisect it in two different angles. While the angle bisector CO bisects it into two angles that are theta and theta, angle bisector CP bisects it into other two angles that are equal to alpha and alpha. And this is impossible. Why? Because if, for example, angle C equals to 30 degrees, any angle bisector of this angle C that is equal to 30 degrees, will bisect it only to 15 and 15 and not to any other angles. While here we found out that angle C will be bisected into two different angles. Okay? So it is a contradiction, and due to the contradiction, we conclude that our assumption is incorrect, and therefore, if our assumption is incorrect, then we will conclude that CO indeed passes through point P. So we finish with the proof that CO passes through point P. Then it focused on this triangle ODC. This angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle, especially in triangle ODC. Likewise, in triangle PLC, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees, exactly for the same reason that is equal to 90 degrees minus theta. This angle must be equal to 90 degrees minus theta. So then, in the next step, we proved that the triangle PLC is similar to triangle ODC. So why those two triangles are similar to each other? First of all, again, triangle PLC is similar to triangle ODC. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. Finally, we have angle theta, that is a common angle that belongs to both triangles, so this angle equals to itself. So we actually found out that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We will conclude that PL in the big triangle over OD in the small triangle is equal to LC in the big triangle over DC in the small triangle. Repeat again, we conclude that PL over OD equals to LC over DC. PL equals to R. OD equals to 1, it is the radius of the small circle. LC, what is the value of LC? LC equals to 3 plus 1, that is 4, and 4 plus 3 is 7, plus LF. So LC equals to 7 plus LF, so we substitute LC by 7 plus LF over DC. DC equals to 3 units. Substitute DC by 3 units. So in conclusion, found out that according to equation number 1, R equals to 7 plus LF over 3 here. We multiply this equation number 1 by 3, and found out that 3R equals to LF plus 7. We subtracted 7 from this equation. We found out that LF equals to 3R minus 7. So you can write down that LF equals to 3R minus 7. Then, because of the fact that the side length of the square is equal to 3 units, we will examine 3 possibilities for the value of the radius of this circle. Either the radius of this circle will be less than 3 units, the radius of this circle could be equal to 3 units, or the radius of this big circle will be greater than 3 units. So we have the first possibility that the radius of the big circle is less than 3 units. If the radius of the big circle is less than 3 units, so here R is less than 3 units. Therefore, what the square is equal to 3 units. So here the side length of the square will be higher than the radius, because the radius is less than 3 units. So here we have 1, 2, 3 right angles. Why this angle equals to 90 degrees? It is equal to 90 degrees according to rule number 1. The radius is drawn to the point of tendency, therefore this angle equals to 90 degrees. So in quadrilateral PTLF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrilateral PTLF that has 4 right angles is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PT equals to LF, PT equals to LF. But here, PT equals to R. PT equals to R, and from this equation, R equals to PT equals to LF, we will derive that LF equals to R. LF equals to R. So from one side, LF equals to R. From the other side, LF equals to 3R minus 7. So here, from this equation, R equals to LF equals to 3R minus 7, we will derive that R equals to 3R minus 7. Here, we subtracted R from this equation, and found out that R minus R is 0 and 3R minus R is 2R. So in conclusion, we found out that 0 equals to 2R minus 7. We added 7 to this equation and found out that 2R equals to 7. We divided this equation by 2 and we found out that R equals to 3.5 units. But according to our assumption, R is less than 3 units. R cannot simultaneously be equal to 3.5 units and be less than 3 units. So due to the contradiction, we cancel the possibility that R is less than 3 units. Then we have the second possibility that R is equal to 3 units exactly. If R equals to 3 units, it means that the side length will be exactly the same height of the radius, that is equal to 3 units. So in quadrilateral PKLF, we have 1, 2, 3 right angles. Again, this angle equals to 90 degrees according to rule number 1. The radius is drawn to the point of tendency, therefore this angle equals to 90 degrees. So in quadrilateral PKLF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So in quadrilateral PQLF, we have 4 right angles, therefore quadrilateral PQLF is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PK equals to LF. But here, PK equals to 3 units, because according to our assumption, R equals to 3. So PK equals to 3, and from this equation, 3 equals to PK equals to LF, we will derive that LF is also equals to 3 units. LF equals to 3 units. So from one side, LF equals to 4 units. From the other side, we have already found out that LF equals to 3R minus 7. So from this equation, 3 equals to LF equals to 3R minus 7, we will get that 3 equals to 3R minus 7. Here, we added 7 to this equation, and we got that 3 plus 7 is 10, so we found out that 10 equals to 3R. We divided this equation by 3, and we found out that the radius of this big circle equals to 10 over 3, that is 3 and a third. But here we have a contradiction, because R cannot both be equal to 3 and also be equal to 3 and a third. Due to the contradiction, we cancel the possibility that R equals to 3 units. Okay, then we have the last possibility that R is greater than 3 units. So if R is greater than 3 units, it means that the radius will be higher than the side length of the square, that is 3. Okay, so here from point K we go perpendicular on the radius PL. Okay, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So in quadrilateral KTLF we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral KTLF, we have 4 right angles. Therefore, quadrilateral KTLF is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, TL equals to KF. TL equals to KF. But here, KF is the side length of the square that is equal to 3. And from this equation, TL equals to KF equals to 3, we derive that TL is also equals to 3. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that TK equals to LF. TK equals to LF. But we have already found out that LF equals to 3r minus 7. So from this equation, TK equals to LF equals to 3r minus 7, we derive that TK is also equals to 3r minus 7. Here, TK equals to 3r minus 7. And what is the value of PT? From the domain, it is very easy to see that PT equals to PL minus TL. PT equals to PL minus TL. PL equals to R and TL equals to 3, therefore PT equals to R minus 3. So we found out that PT equals to R minus 3, TK equals to 3R minus 7. We join points P and K together by a straight line. Point P is the center of the circle, point K is the point on the circle itself, therefore PK is the radius of the circle, the big circle that is equal to capital R. Then I copied the right green triangle in a new page and we implemented the Pythagoras theorem on the green right triangle, triangle PKL, triangle PKT. Okay. So this is the green right triangle that I copied from the original drawing. Here we implemented the Pythagoras theorem on this green right triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PK, therefore the square of the hypotenuse is PK square. It must be equal to PT square plus TK square. PK equals to R, therefore PK square is R square. PT equals to R minus 3, therefore PT square is 1R minus 3 square. TK equals to 3R minus 7, therefore TK square equals to 3R minus 7 square. Here we open the brackets on this side of equation number 1 and found out that R square equals to R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3, that is minus 6R, plus 3R minus 7 square is 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, times 7 is minus 42R. Here we have R square on both sides of the equation, so R square will get cancelled. In this side of the equation, nothing is left after we cancel R square, we have 0, that is equal to, here we have 9R square, minus 42R, minus 6R is minus 48R, and 9 plus 49 is 58. So in conclusion, we got the quadratic equation that 0 equals to 9R square plus 48R plus 58. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to b, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58, and the variable that we are looking for in our quadratic equation, in our specific quadratic equation, is r, so x equals to r. So we put the data inside the formula for x, and we found out the value or the values of r because x equals to r. So here r equals to minus b, b equals to minus 48, therefore minus b is minus 48, that is actually 48. And it is equal to square root of b squared. B is minus 48, therefore b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 36, times c. C is 58, so minus 36 times 58 is minus 2088 over 2a. A is 9, so 2a is 18. So here we found out that r equals to 48 plus minus 2304 minus 2088 is 216. So inside the root we left only with 216 over 18. Okay, so here we have two solutions that are possible for r. The first solution for r is that r equals to 48 minus 40. The square root of 216 is 14.6969. So the first solution for r is that r equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031, and if we divide it by 18, we get that r equals to 1.85. But because of the fact that we have already found out that r cannot be less than 3 units and 1.85 is less than 3 units, we cancel this solution and we left only with the second solution for r, that r equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969, and if we divide it by 18, we get that the radius of this big circle is equal to 3.483 units. Here, I repeat again, that the radius of this big circle is equal to 3.483 units. Okay? Thank you very much.